We've seen previously that the dot product gave us a way to combine two vectors and get some new information about them. We're now going to look at a second way to combine two vectors called the cross product. We saw that the dot product of two vectors produced a scalar. The cross product is different in that it produces a new vector, and that vector is going to be perpendicular to the plane formed by the two given vectors. Because it's a vector, the cross product has both orientation and magnitude. We'll see that cross products are essential for geometry and physics in 3D. And in particular, we're going to examine the way that cross products can be used to calculate something called torque. Some important distinctions between a cross product and a dot product are that first, the cross product is only defined in 3 dimensions. There's no such thing as a cross product of 2-dimensional vectors. When we take a cross product, the result is going to be a vector, not a scalar. We'll see when we find the cross product that the direction of that new vector is important. And in particular, the cross product is going to produce a vector that is orthogonal, which is just another way of saying perpendicular to both of the original vectors, which will have some interesting and useful applications for us. Because the direction of a cross product vector is important, there's a quick and handy rule, no pun intended there, to determine its direction called the right-hand rule. If you wish to find V cross W, then you're going to point your right hand, the fingers on your right hand, in the direction of V, and then curl those fingers towards W. This will twist your hand so that your thumb ends up pointing in the direction of the cross product vector V cross W. If instead you point your fingers on your right hand towards W and curl towards V, it should make sense to you that your thumb would have to point in the opposite direction. So this tells us that W cross V points in the opposite direction of the vector V cross W. Let's take a look now at how we can actually find the cross product by looking at its definition. So V cross W is going to be the vector that we get when we take the determinant of the 3x3 matrix that has I, J, and K as its first row, the components of the vector V, the first vector in our cross product, as the second row, and then the components of the vector W as the components of the third row. We can break that 3x3 determinant down into a series of 2x2 determinants. So our first one, we're going to multiply the vector I, which we know points in the direction of X, by the determinant we get by taking the Y and Z coordinates, or the J and K coordinates, from our two vectors. Then we'll subtract the determinant of the matrix that we get by taking the I and K coordinates and multiply that determinant by the vector J. And then lastly, we'll take the determinant of the matrix that we get by taking the X and Y, or the I and J components of our original V and W vectors, and multiplying by the vector K. One key thing to remember here is that that determinant in the middle, we subtract that one off. If we use our rules for 2x2 determinants, then this breaks down into the formula V2 times W3 minus V3 times W2, which is going to be a number, times the vector I, minus V3 times W1 minus V1 times W3, times the vector J, plus V1 times W2 minus V2 times W1 times the vector K. And we can take those three components, or those three coefficients, and we can write them into the vector form, so that our cross product is going to be the vector V2 W3 minus V3 W2, V3 W1 minus V1 W3, and V1 W2 minus V2 W1. This looks like a lot, but once you do a few of these, you'll see that the pattern starts to establish itself and make sense to you. Let's go ahead and do an example of one of these so we can see how this formula works. So we have the vector V equals 1, 2, 3, and the vector W equals 2, 1, 0, and we want to compute both V cross W and W cross V. So V cross W, We know that's going to be the determinant of the vector ijk, or the determinant of the matrix. Then we're going to put the components of V in the first row and the components of W in the second row. Now we're going to break that down further. I'm going to take the determinant of the matrix I get when I take all of the coefficients that aren't underneath I. So I'm going to take 2, 1, and 3, 0, and I'm going to multiply that determinant by the vector I. I'm going to subtract. This is important to remember. The next one we subtract. Now this time I'm going to take the components of the vector, or the components of the matrix that comes from the things that are underneath I and K. So I'm going to take 1 and 2 and 3 and 0 and multiply that by the vector J. And then lastly, we'll take the things that are underneath I and J. So 1 and 2 and 2 and 1, and we'll multiply that by the vector K. Now you have to remember how to do a 2 by 2 determinant. So remember that if we have a matrix that looks like A, B, C, D, and we're taking the determinant, these absolute value symbols around the matrix are an indication that we're taking the determinant. That's what those mean. And the way we do this is we take A times D and we subtract B times C. So for our first one, we're going to do 2 times 0, which is 0, minus 3 times 1, and we're going to multiply that by I. Then we're going to subtract off what we get when we do 1 times 0, minus 3 times 2, multiply that by J. And then in our last one, we're going to do 1 times 1, minus 2 times 2, and multiply that by K, which means that our cross product is going to be the vector negative 3I plus, because of the two negatives, 6J minus 3K, which if we want to write that using vector brackets, we can write that as negative 3, 6, negative 3. Now, we know that the right-hand rule tells us that W cross V has to be the opposite of that. So we know, starting off, that W cross V, we should end up with the vector 3, negative 6, 3, which points in the opposite direction. But let's go ahead just for the practice and work it out. So now we're going to have I, J, K, and we're going to reverse or flip our rows. So we have 2, 1, 0, and 1, 2, 3. So now I'm going to do the determinant of the matrix 1, 2, 0 with 1, 2, 0, and 3 inside of it times I minus 2, 1, 0, 3 times J. Those come from the columns underneath I and K. And then we take the columns underneath I and J and multiply that by K. And using our rules for determinants, we get 3 minus 0. Notice that's the opposite of what we had the previous time. Then minus 6 minus 0 times J plus 0 minus. Did I write this one wrong? I did. I wrote the wrong entries in this matrix. I don't know what I was thinking. I'm going to take the things underneath 2, 1, 1, 2. So this should be 4 minus 1 times K. And we do, in fact, end up with 3I minus 6J plus 3K, which is the vector 3, negative 6, 3. This is a 1 here. It looks like a 0 there, but that's a 1. All right, I'm not going to spend any time demonstrating why these are all true, but I am going to show you now some properties of the cross product that can be useful. We've already seen the first of these, which is that U cross V is the negative of V cross U. We're going to refer to that as the anti-commutative property of the cross product. Next, we have an associative property of the cross product, which says that if we multiply U by some scalar A and we multiply V times some scalar B, then that is going to give us, when we take the cross product of those two vectors, we get A times B times the cross product of U cross V. Then we have two different versions of the distributive property. The first of those is that if we take a vector u and we cross it with the sum of two vectors v plus w, then that becomes the sum of the cross products, u cross v plus u cross w. And similarly, if we change the position of some things around in there, if we take the sum of two vectors, u plus v, and we cross that with the vector w, then that is once again the sum of the cross products, u cross w plus v cross w. We've seen previously that the dot product, v dot w, was equal to the magnitude of v times the magnitude of w times the cosine of theta. It turns out that the magnitude of the cross product, which is going to be a scalar, the cross product is a vector, but when we take its magnitude, we get a scalar. The magnitude of the cross product is going to be the magnitude of v times the magnitude of w times the sine of theta. So this is another useful tool we have for finding the angle between two vectors. So let's look at an example of that. All right, we know that the magnitude of the cross product is going to equal the magnitude of v times the magnitude of w times the sine of theta, which gives us then, by rearranging, that the sine of theta is going to be the magnitude of v cross w divided by the magnitude of v times the magnitude of w. So we have a few things to figure out here. First of all, let's find the cross product. We know that that is going to come from the determinant of this matrix. We'll write v in the first row and w in the second row. So now we get the magnitude of, or the determinant of the matrix 1, negative 1, 4, 2, negative 2 times I, minus the determinant of 3, 1, 2, negative 2 times j, plus the determinant of 3, 1, negative 1, 4 times k. Working that out by multiplying, we get 2 minus 8 times I minus negative 6 minus 2 times j plus 12 minus negative 1, so plus 1 times k, which is the vector negative 6. I don't need parentheses anymore. Negative 6i plus 8j plus 13k. And so now we can take the magnitude of that. The magnitude of v cross w is going to be the square root of 36 plus 64 plus 169, which is the square root of 269. Now the magnitude of v is going to be the square root of 9 plus 1 plus 4, which is the square root of 14. And the magnitude of w is going to be the square root of 1 plus 16 plus 4, which is the square root of 21. So now we know that the sine of theta is going to be the square root of 269 divided by the square root of 14 times the square root of 21. Getting out my handy dandy calculator here. I am getting there that the sine of theta is 0.956 0.9565, which means that theta is going to be the inverse sine of that number. And again, I'm rounding in both of these. I'm going to take, the inverse sine of that number. And I'm going to do this in radians first. So in radians, we get that theta is 1.27 radians, which is a very hard number to fathom. Or if we do that in degrees, we'll get that theta is approximately 73.05 degrees. Okay, so at this point, we know how to compute a cross product. And we've seen that we can use it to find the angle between two vectors. But the really important thing about the cross product is its geometric meaning. That's going to be very helpful to us. So one important thing to note is that the magnitude of the cross product is equal to the area of the parallelogram that we would get if we use the two vectors, we place them tail to tail. If we use those two vectors in the plane and form a parallelogram with those vectors as two of the sides, the cross product automatically gives us the area, the magnitude of the cross product gives us the area of that parallelogram. If we get 0 for our cross product, that automatically tells us that the vectors we're working with are parallel to one another. And last, but certainly not least, perhaps the most important thing about the cross product is that its direction is always normal, which is another way of saying perpendicular to, right? We've got orthogonal, normal, and perpendicular, but the vector that the cross product forms is always a normal vector to the plane formed by the two given vectors, which means that that vector, the cross product vector, is perpendicular to both of the vectors that you started with, both of the vectors that you used to compute the cross product vector. We'll take a look at some examples of the area of a parallelogram and the use of parallel vectors and the cross product in the next video. But for now, let's take a look at an example of this idea that the cross product produces a perpendicular vector. Here we are asked to determine one vector that is perpendicular to the plane spanned by the two vectors v equals 3, negative 1, 2, and w equals 1, 4, negative 2. And so we know that by taking the cross product of those, we produce a vector that has that property. So a simple answer, a straightforward answer to this question is that our vector v cross w is automatically perpendicular to both of these. It's perpendicular to the plane, which means it's perpendicular to any vector contained in that plane. So we'll go ahead and compute v cross w. And so that's going to be, again, we use the determinant definition, 3, negative 1, 2, 1, 4, negative 2. So we're going to take the determinant of negative 1, 4, 2, negative 2 times I minus 3, 1, 2, negative 2 times j plus 3, 1, negative 1, 4 times k, giving us 2 minus 8 times I minus negative 6 minus 2 times j plus 12. Now, if you're noticing that this is the same vectors we used in the last example, you're correct. Plus 1 times k. And so we end up with the vector negative 6i plus 8j plus 13k, which we can write as the vector negative 6, 8, 13. And it's also the case that any multiple of that vector, except for the 0 multiple. So this was v cross w, works. And notice we could also do w cross v. W cross v would work just as well. It would just be pointing in the opposite direction, but still perpendicular to our two original vectors and therefore perpendicular to the plane that those vectors span. So wrapping up what we've learned here, the cross product is going to produce a vector, and that vector is going to be perpendicular to the vectors that we started off with, the vector whose cross product we're determining. The right-hand rule, if you take the fingers of your right hand, point them in the direction of your first vector, and then curl them towards the second vector, that's going to force your thumb to point in the direction of the cross product vector. Only works if you use your right hand, otherwise it would be a very foolishly named rule. And then last I told you that the magnitude of the cross product measures the area of a parallelogram. We'll investigate that last idea a little more thoroughly in the next video, where we're going to look at applications of the cross product, including area, torque, and collinearity.